Alrighty. Okay. Where was I? Oh yes, traits. I just double check so I remember. Type's behavior consists of the methods we can call on a type. Right. Different types share the same behavior if we can call the same methods. Oh yeah. So even if we have different variables of different types, we can format the expected outputs of shared methods they might have. Multiple strokes. That hold various kinds and amounts of text. We want to make a media aggregator library create named aggregator that displays summaries of data. To do this, we need a summary from each type, and we'll request that summary by calling a summarize method. Shows a definition of a public summary trait that expresses this behavior. Public trait summary, and it contains a function summarize which outputs a string. We declare a trait using the trait keyword, and then the trait's name, which is summary in this case. We also declare the trait as pub so that the crates depending on this crate can make use of this trait too. Yes, of course, we want it to be public. Inside the curly brackets we declare the method signatures that describe the behavior. In this case, fn summarize self outputs a string. After the method signature, instead of providing curly brackets, we use a semicolon. Each type implementing this must provide its own custom behavior for the body of the method. Okay. Yeah. Got it. That's fine. A trait can have multiple methods in its body. Method signatures are listed one per line and each line in semicolon. Okay. And so the example of that is news article, social post, both public structs, and they both implement their own version of summarize, which must be a string. Yeah, it's okay. Here's an example. Yeah, it just uses summarize. And the post is a social post, so yeah, that's fine. This code prints one new post. Horse books. Of course, as you probably already know, people. Yeah. Simple enough. Alright, let's move on. One restriction is that we can implement a trait on a type only if either the trait or the type are local to our crate. Ah, yeah, I remember now. Okay. But we can't implement external traits on external types. We cannot implement the display trait on vector within our crate because display and vec are both defined in the standard library and are not local to our aggregator. This is called coherence. More specifically, the orphan rule, because the parent is not present. Okay. Let's move on then. Default implementations. What do we have here? Sometimes it's useful to have default behavior for some or all of the methods in a trait, instead of requiring implementations for all methods on every type. Then, as we implement the trait on a particular type, we can keep or override each method's default behavior. For example, we specify a default string. Yeah. Okay. So every struct that contains a summary that contains a summary method is forced to use this, or they have to overwrite it. To specify the default implementation, we specify an empty implementation block with implementation summary for news article brackets. Nice. Which would be where? I guess they didn't include it here. An empty implementation block with summary for news article. So up here, this would be just 2 brackets. Even though we're no longer defining the summarize method directly, we've provided a default implementation. Yeah, so it's going to call the read more default value. Okay. What else do we have? Default implementations can call other methods in the same trait, even if those other methods don't have a default implementation. In this way, a trait can provide a lot of useful functionality and only require implementers to specify a small part of it. For example, we could define the summary trait to have summarize author method, whose implementation is required, and then define a summarize method that has a default implementation that calls the summarize author method. So what is it talking about? So the implementation for summary would be summarize author, and then inside of that so we have a summary trait which is like this: summarize author and summarize, and then when we implement it on a type, we do implement summary, and we just give it a different method body. Oh, actually there's no method body defined here, it's just defining the function. Here we're defining the content, but in this one we're doing a default implementation. Okay. So it's mixing and matching. We can call summarize on instances of the social post struct, and the default implementation of summarize will call the definition of summarize author we've provided. Okay. Because we've implemented summarize author, the summary trait has given us the behavior of the summarize method without requiring us to write any more code. Here's what that looks like. Yeah, makes sense. So you need to use an at here. Okay. I don't know why that's important. Oh, it is for this output, I guess. Alright, makes sense. Traits as parameters. Now that you know how to define and implement traits, we can explore how to use them to define functions that accept many different types. We'll use the summary trait. We implemented on the news article and social post types in listing 1013. To define a notify function that calls the summarize method on its own, on its item parameter, which is of some type that implements the summary trait. Okay. And to do this, we use the implement trait syntax like this. So we have public function notify, and the parameter is called item, and it's a reference to implement of summary. Okay. So instead of a concrete type for the item parameter, we specify the implement keyword and the trait name. This parameter accepts any type that implements the specified trait. In the body of notify, we can call any methods on item that come from the summary trait, such as summarize. Okay. We can call, notify, and pass in any instance of news article or social post. Code that calls the function with any other type, such as string or an I32, won't compile because they don't implement summary. Yep, makes sense. The implement trait syntax works for straightforward cases. But it is actually syntax sugar for a longer form known as trait bound, which looks like this. Okay. So public. Oh, I see. So it's actually achieving the same thing as this. Which is T summary. And item of that summary in reference to T. Oh, it gets more complex. For sure. This longer form is equivalent to the example, but it's more verbose. Replace trait bounds with the declaration of the generic type after a colon and inside angle brackets. Implement trait syntax is convenient and makes for more concise code in simple cases, while the fuller trait bound syntax can express more complexity. For example, we can have two parameters that implement summary. Doing so with implement trait looks like this. Yeah, and using implement trait is appropriate if we want this function to allow item 1 and item 2 to have different types, as long as both types implement summary. If you want to force both parameters to have the same type, however, we must use a trait bound. Wow. Yeah, it makes total sense. Holy shit. That's great. Because both of these need to be the same if they want to reference this. However, in this case, it's completely separate. Okay. Multiple trait bounds with the plus syntax. We can also specify more than one trait bound. So we want to say we want to notify to use display formatting as well as summarize on item. We specify in the notify definition that item must implement both display and summary. You can do so using the plus syntax. Wow, that's crazy. Holy shit. Using too many trait bounds has its downsides. Each generic has its own trait bound, so functions with multiple generic type parameters can contain lots of trait bound information between the function's name and its parameter list, making the function signature hard to read. For this reason, the Rust has alternate syntax for specifying trait bounds inside a where clause after the function. So instead of writing this, which is display and clone and debug, we can use a where like this. tu T equals T reference, U equals U reference, where T is display, U is clone debug. Display and clone. Wow. I see. It's less cluttered. In terms of actual writing though, this one actually has more writing, I think. But it is easy to read. That is true. Alright. Returning types that implement traits. So we can also use the implement trait syntax in the return position to return a value of some type that implements a trait. Okay, so it's going to output an implement summary. Wow. By using implement summary for the return type, we specify that the return summarizable function returns some type that implements the summary trait without naming the concrete type. In this case, return summarizable returns a social post, but the code calling this function doesn't need to know that. Oh, I see. Yeah, because there's no specification or social post in the method signature. For the inputs, at least. Wow. This is pretty deep. Jesus. Ability to specify return type only by the trait it implements is especially useful in the context of closures and iterators, which we cover in chapter 13. Closures and iterators create types that only the compiler knows or types that are very long to specify. The implement trait syntax lets you concisely specify that a function returns some type that implements the iterator without needing to write out a very long type. However, you can only use implement trait if you return a single type. For example, this code would not work. Oh, so it's news article and social post. You can't have either or. You have to pick one. Interesting. Returning either a news article or a social post isn't allowed due to restrictions around how the implement trait syntax is implemented in the compiler. We'll cover how to write a function with this behavior at the end of chapter 18. Okay. Using trait bounds to conditionally implement methods. Oh, wait a minute. Oh. Quick break. Need a quick break just to refresh my whatever needs refreshing. My brain. Ah, you fucking. Alright, I'm just gonna do an all-out attack then. Screw it. Bro. Alright, you win. I played myself. Oh, that was difficult. Mating 6. Well, I saw this, but then I thought I could do that, but then I guess it's just a longer way. What's the faster way? Oh, I just bring the rook in. Okay, whatever. Anyways. Right. Now that I'm even more tired, I think I'm fully rested. Let's begin. Using trait bounds to conditionally implement methods. By using a trait bound with an implement block that uses generic type parameters, we can implement methods conditionally for types that implements the specified traits. I have no idea what that means. For example, type pair t always implements the new function. To return a new instance. Self is a type alias for the type of the implement block, which in this case is pair t, but in the next implementation block, pair t only implements the CMP display if its inner type t implements the partial order trait that enables comparison and the display trait that enables printing. Whatever that means, let's look at the example. So it's using the display library. we have a struct called pair. It's not called pair, sorry, it's a is it called pair? I guess it's called pair. Struct called pair of type T. And there's an X and a Y that are both T. So this could be anything. Integer, floating point, I guess. Now I want to implement T parity. So this means it implements for all types of T, and it's taking parity. I mean, it's defining the method for parity, and then we need a new function. Function new xt yt, and it outputs itself, and that will be x and y. Then in the other side of it, so this is implementing two things, new and CMP display. But in the CMP display implementation, in this method, the type T must also include display and partial odd. And it's designed for the parity struct. So the function name is CMP display. It takes a reference of itself. Now if the self.x is greater or equal to, is greater than or equal to self.y, then the largest member is x, and the value of x is displayed. Otherwise, the largest member is y, and the y value is displayed. And this doesn't return anything, it just prints. Okay, we can also conditionally implement a trait for any type that implements another trait. Jesus. Implementations of a trait on any type that satisfies the trait bounds are called blanket implementations and are used extensively in the Rust standard library. For example, the standard library implements the toString trait on any type that implements the display trait. The implementation block in the standard library looks similar to this code. Implement T type display toString for T. Because the standard library has this blanket implementation, we can call the toString method defined by the toString trait on any type that implements the display trait. That's the trait, yeah. And inside this trait, or whatever variables using this trait, must have a toString method. But according to this, they must also implement the display trait. Holy shit, this is pretty deep. For example, we can turn integers into their corresponding string values like this, because integers implement display. Oh, I see. So because this is an integer, this check passes. So this is valid. And defining it for t, which is all types. And it has toString. Blanket implementations appear in the documentation for the trait in the implementers section. Traits and trait bounds let us write code that uses generic type parameters to reduce duplication, but also specify to the compiler that we want the generic type to have particular behavior. Yeah, of course. That was a lot, to be honest. And this is a lot as well. Lifetimes. Holy shit. Alright. Let's have a quick look. Lifetimes. Validating references with lifetimes. Lifetimes are another kind of generic that we've already been using. Rather than ensuring that a type has the behavior we want, lifetimes ensure that references are valid as long as we need them to be. One detail we didn't discuss in chapter 4 is that every reference in Rust has a lifetime, which is the scope for which that reference is valid. Yes, I remember that. Most of the time, lifetimes are implicit and inferred, just like most of the time types are inferred. We are only required to annotate types when multiple types are possible. In a similar way, we have to annotate lifetimes when the lifetimes of references could be related in a few different ways. Rust requires us to annotate the relationships using generic lifetime parameters to ensure the actual references used at runtime will definitely be valid. Annotating lifetimes is not even a concept most other programming languages have, so this is going to feel unfamiliar. Although we won't cover lifetimes in their entirety, we'll discuss common ways you might encounter the lifetime syntax, so you can get comfortable. Preventing dangling references with lifetimes. The main aim of lifetime is to prevent dangling references, which cause a program to reference data other than the data is intended. Okay. The examples declare variables without giving them an initial. Hang on a sec. I need to do something. Right, note that the examples declare variables without giving them an initial value. Yes. So the variable name exists in the outer scope. Yes. At first glance, this might appear to be in conflict with Rust having no null values. However, if we try to use a variable before giving it a value, we'll get a compile time error, which shows that Rust indeed does not allow null values. Okay. The outer scope declares a variable named r with no initial value, and the inner scope declares a variable named x with 5. Yep. We attempt to set the value of r as a reference to x. Then the inner scope ends and we attempt to print the value in r. This code won't compile because the value that r is referring to has gone out of scope. X does not live long enough. Yep, makes sense. Makes total sense. The error message says that X does not live long enough. The reason is that X will be out of scope. Yep, okay. I would be referencing memory that was deallocated when X went out of scope, yes. So how does it determine it's invalid? It uses a borrow checker. The borrow checker. The Rust compiler has a borrow checker that compares scopes to determine whether all borrows are valid. Here we've annotated the lifetime with lifetime of R with A and the lifetime of X with B. As you can see, the inner B block is much smaller than the outer A block. Rust compares the size of the two lifetimes and sees that R has a lifetime of A, but that it refers to memory with a lifetime of B. Program is rejected because B is shorter than A. The object of the reference doesn't live as long as the reference. This fixes the code so it doesn't have a dangling reference. Let x equal 5, r equals reference to x. Yeah, okay. Now that you know where the lifetime of references are and how Rust analyzes them, let's explore generic lifetimes of parameters and return values in the context of functions. Okay. Generic lifetimes will write a function that returns the longer of two string slices. This function will take two string slices and return a single string slice. After we've implemented the longest function, the code in listing 1019 should print the longest string is ABCD. So you've got string 1, ABCD, string 2, XYZ. Longest. So it's going to compare these two. And it's going to say this one is longer, so it's ABCD. Note that we want the function to take string slices, which are references rather than strings, because we don't want the longest function to take ownership of its parameters. Okay, yeah. That makes sense. Refer to chapter 4 for more. If we try to implement the longest function as shown in listing 1020, it won't compile. And the reason it won't compile is it's missing a lifetime specifier. This function's return type contains a borrowed value, but the signature does not say whether it is borrowed from X or Y. Oh, interesting. Because it's going to return either X or Y. The help text reveals that return types need a generic lifetime parameter on it. Because Rust cannot tell whether the reference being returned refers to X or Y. Actually, we don't know either, because the if block, yeah. When we're defining this function, we don't know the concrete values that will be passed into this function, so we don't know whether the if case or the else case will execute. We also don't know the concrete lifetimes of the references that will be passed in, so we cannot look at the scopes as we did previously to determine whether the reference we return will always be valid. True. The borrow checker cannot determine this either, because it doesn't know how the lifetimes of X and Y relate to the lifetimes of the return value. To fix this error, we'll add generic lifetime parameters that define the relationship between the references, so the borrow checker can perform its analysis. Lifetime annotation syntax. Lifetime annotations don't change how long any of the references live, rather they describe the relationships. Oh, that's a lot easier to manage, actually. Just as functions can accept any type when the signature specifies a generic type parameter, functions can accept references with any lifetime by specifying a generic lifetime parameter. So let's see. Lifetime annotations have a slightly unusual syntax. The names must start with an apostrophe and are usually all lowercase and very short. Most people use the name apostrophe A for the first. We place lifetime parameter annotations after the ampersand on a reference, using a space to separate annotation for reference type. Okay. So it's just an apostrophe. Alright, pretty cool. I have to get off now, actually. So let's end it here. Pretty good progress today, I would say. Not too much.